Good evening, everybody. Tonight we're dealing with a problem that is challenging in the sense the numbers are very, very large and the calculations would be almost impossible to do by hand. Now, let me give you an example. I think you guys are familiar with this notation. We're trying to show that this numerator is a multiple of 13. If it is, that means it would be a natural number, a positive integer. A simpler example with smaller numbers, 91 over 13 is equal to 7, right? And 7 is a proud member of the natural numbers, right? Or the positive integers, okay? So again, this is a fancy way of saying show that the numerator here, 2 to the 1/90th plus 3 to the 46, is a multiple of 13. And that would establish that, 13 would cancel, and this would be a natural number. Now, another way to write this is in the modular arithmetic format. This is equivalent. If we can work in this kind of equality format, this is a congruent symbol. This really says that 2 to the 1/90th plus 3 to the 46 quantity minus 0 is divisible by 13. In other words, that says it's a multiple of 13, and it confers the benefit of dealing with a symbol that has more or less the same properties as equality. Okay. Now, what we're going to do is just carry on, and we're going to make the assumptions everything is modulo 13 arithmetic. And just an example, 29 is 2 modulo 13 because 29 is equal to, 29 is 3 modulo 13 since 29 is equal to 2 times 13 plus 3, okay? So when you're doing modular arithmetic 13, you're dealing with numbers in the range 0 through 12 integers because those are the only possible remainders when you divide any integer by 13. Now what we're doing now is just trying to create conditions where we can reduce this left-hand side and see that it's manifestly a multiple of 13. 3 cubed is equal to 27, but notice that's congruent to 1. 27 minus 1 is divisible by 13. 27 minus 1 is 26, right? Okay, so what does that mean? It means we can use laws of exponents. 3 cubed is the same thing as 1 mod 13. So 3 cubed is again, we'll use the word equal. I'll say congruent, but it has very much the same properties as equality. Okay, so 3 cubed is congruent to 1. We can put it right there, and all we're left with is 3. Notice 3 times 15 is 45, and this is 1, right? And that gives you the 46 that you see right here. Okay, so that's an example of some fairly simple modular arithmetic. So what do we know? We know that 3 to the 46, right? We can already say that right here. 3 to the 46 is congruent to 13, or congruent to 3, sorry here. Let me get this, let me erase this. 3 to the 46 is congruent to 3, and we'll write it right underneath, right? Okay, that's what we've just shown right here, folks. 3 to the 46 is congruent to 3. All right, now let's take a look at 2 to the 4th. All right, now it's kind of hard to know where to go here. I went ahead and I wanted to keep the number small, and so 2 to the 4th is 16, which is congruent to 3, which at least is a single-digit number. Now, if you cube both sides of this, in other words, this part right here is just 2 to the 4th cubed, right? Properties of exponents, 3 copies of 4 copies is 12 copies, right? All right, and then you cube the 3, you get 27, and we already know that's congruent to 1, right? So we got that far. Now with 2, folks, and again, we're doing 2 because we've already handled 3. Right now we're worried about 2. All right. Now, so let's take a look here. What does that do for us? Well, we know that 2 to the 12th is congruent to 1. Okay. So we also know that 12 times 50 is 180, right? In other words, you can 12 times 15 is 180. And 180 plus 10 is 190, right? And that's just laws of exponents. So you see this part right here would just be, just in modular arithmetic, this is a slightly sloppy, but it's 1 to the 15th, right? In modular arithmetic. All right. And so we have 2 to the 10th. And just like we did earlier, we just working a little bit harder here. 2 to the 4th is congruent to 3. So this right here would be 9 times 4 right here. Okay, And 36 is congruent to 10. 36 minus 10 is 26, which is 2 times 13, right? Okay, so now we know that 2 to the 1/90th is congruent to 10, and so we can put that right here. But 10 plus 3, you see this is as easy as it gets, right? 10 plus 3 is equal to 13, which is certainly congruent to 0. And so we finished. We are done. Okay, we proved what we set out to prove using modular arithmetic. Now, some of you may be saying, well, there's something called the Euler's Totient function. That's exactly right. What you could have done without I just kind of did it manually here. But what you can do is consider this object that's called the Euler Totient function. And it counts the number of values that are relatively prime. Now, phi at 13 turns out to be equal to 12. All right. The same 12 that you see here that we just kind of figured out manually, okay? Phi at 13 is equal to 12. And there's a result called the Euler result, I guess, that says that a to the phi of n, and I'll just do this generally, is congruent to 1, provided that a and n are relatively prime, okay? So that's called the Euler Totient function, and this would be with the stipulation that a and n are co-prime, share no common factors. So we could have gone that route, but here we just manually handled things. We got to a situation where we had a tractable single-digit exponential circumstance here, and then once we raise this to the 27th power, once we raise this to the third power, we get 27, and it's clearly congruent to 1. So we kind of just did Euler's totient function by hand. It's not always easy to do what I've done here with larger numbers, and using the Euler totient function would be advantageous. But in any event, we finished the problem right here. Let me know what you thought.